Okay, any thoughts from anybody? Any suggestion, any solution?
Sir, am I audible?
Very low, but yeah, I can hear you.
Yeah. Now is it better?
Yes, better, yes.
Sir, so there are two classes, but the partitioning has been done into four hyperspheres. So like, what is the basis of partitioning here? Sir, the question's first sentence says that the data set is like n features and two classes.
Right.
And then the data set has been partitioned into four hyperspheres. So like, what is the basis of partitioning here?
So partitioning, basically every hypersphere will contain points from one class only. Okay, which you cannot do using two hyperspheres.
As this means that the hypersphere, like one hypersphere will not contain more than one class. So like two
Yeah,
hyperspheres will.
exactly. Exactly. That's what I mentioned in the problem statement here.
So like, can we assume that that it's like 50-50, like two hyperspheres are one class and two hyperspheres are another class?
Yes, you can assume that. Yep. Yeah, assume that. Yes.
Sir, excuse me, sir. Sir, the size of the set produced by condensed KNN in the best case would be 4.
Sorry, say again.
Sir, in the question it was mentioned, it is mentioned that what would be the size of the set produced by the condensed KNN in the best case.
In the best case scenario, yes.
So I think the size will be 4.
Okay, all right. Let me hear from others. What others say? Yeah, I note your solution. Yeah.
Sir, I think it will be 2.
It will be 2. Okay, all right. Any other response?
Sir, even I think it is 4. So it should be 4, I guess.
4. Okay, any other response? Okay, so yeah, so let me try to understand a student who said 2. So can you please reason why you said 2?
Actually, sir, I'm not sure about it, but with 2 data points, I mean, we can create a plane or a hyperplane kind of thing which divides the hyperspheres into 2 categories, one with one class and the other with other class.
If that is possible, that is a possibility, then you would have created only 2 hyperspheres rather than 4, right? So the reason that you have 4 hyperspheres, you cannot do that.
Okay, sir.
Okay.
Actually,
So
sir,
in my
it's
opinion,
difficult to visualize these hyperspheres. I mean,
yeah, hyperspheres are always difficult to visualize. Like anything beyond 3, you difficult to visualize. Okay, so. But hypersphere typically that like you can think about spheres on high dimension, and the radius, definition of radius, of course, the normal definition of radius that you have from centroid to the farthest point. Okay, so in my opinion, the answer would be 4. So the 4 would be correct answer.
Sir?
Now, yeah.
Yeah. So, sir, like this was the fundamental doubt, like which I was having, which kinds of get highlighted in the answer between 2 and 4. So, like when we are dividing into 4 hyperspheres, so
Right.
in the best case here we are assuming that best case as in we are like we could have for the best case we could have both the like it could be linearly separable, like the 4 hyperspheres could be linearly separated into groups of 2 hyperspheres.
In one side
yes,
of
sir.
this and the other
That's
side
what
of this.
that's what I assumed, sir, when I considered 2.
Okay, under
Like-
that assumption, yes, it would be 2. Yes.
Like if we consider best case locally within a hypersphere, then the answer would be 4. But if we consider a best case globally, then the answer could be 2.
Yeah, that's correct. Under that scenario, it would be 2. Otherwise, it is 4. Yeah. Okay.
Sir, can you please explain what Kshitij told just now? Like, I'm not clear with the which he said.
So
Also,
How?
sir, it would be better if you explain
he is saying that if the placements of the hyperspheres is such a way that you can actually partition the two, like 2 and 2 hyperspheres using a straight line, okay, or like hyperplane. One side of this hyperplane you have the two hyperspheres from the same class, and from the other you have the two from the other class. Okay, in a scenario like this, you can have a condensed set with only 2 points. Right, that's what I think you mentioned, right? The student who mentioned.
Yes, sir.
Yeah, okay.
Also, sir, it's not clear what would be the nature of the dividing boundary if the answer is 4.
So answer is 4. So in a situation where you cannot draw a single hyperplane to divide the two class, okay?
Sir, I have a different opinion with what, why 2 can't be the answer, because in the question it's mentioned that all the points are in the hyperspheres. So, uh, it is not possible for the points to exist outside the hypersphere, so that it virtually creates a separation between two classes.
Think about this. So say I think about it this way. So the first you think about this. The first hypersphere, okay, from one class, just beside this one. So assume that all the centroids of the hypersphere are on a single line. Okay. Think about this way. Okay. Now, if that is the case, then first consider from left to right. So the first hypersphere from class number 1, second is from the class number 2, third is from class number 1, fourth is from class number 2. In a scenario like this, don't you think this is possible?
Sir, but the answer here should be 4, right? Like independent of the data, if we take 4 points, we can always classify it. But that is not the case with 2 points. It happens only when there is a particular pattern in the data, right?
That is true, but I didn't say anything about, so only I have talked about hyperspheres, 4 hyperspheres and all. So what are the placements of the hyperspheres? Now, student who mentioned that in a best possible scenario, if the hyperspace happen to be on one side of the straight line, for example, not like the case that I mentioned just now, then you can have 2 points only to cover the whole thing.
Hello, sir.
Yeah, go ahead.
My question remains unanswered actually. I wanted to know what would be the nature of the dividing boundary if the spheres are arranged in such a way that the answer is 4. So is it like there are two hyperplanes
It's of
and
course non-linear. You need to have a card rather than linear separator. Okay, think about it this way. Now forget about hyperspace and all. So you have 4 points. Okay, just 4 points sitting on a straight line. Okay, 4 points, 1, 2, 3, 4 sitting on a straight line. So first point is extreme left point is from class number 1, then class number 2, then class number 1, then class number 2. Now, would you be able to separate this whole thing using a kind of linear separator?
no, sir?
Yeah, you need to have a non-linear separator. So, right?
So even when both the classes are on the same side, we still, in some cases, we need 4 points, right? Like let us assume that, let us take a class 0, like both the classes are 0, which are
So
adjacent.
the
And
question is about in the best case. You look at the last line of my question. In a best case scenario, what can happen? Okay.
yes, sir.
Yeah. Okay. Okay. Now come to question number 1. This is fairly numerical question. Yeah, go ahead.
I have uploaded a image that will like help in clarifying if both of them are on the same side, then why only 2 points can be the best case scenario.
You are in favor of 2 points or against 2 points?
Sir, in the favor of 2 points, like
Yeah.
Ravi was saying that it will depend on the distribution of data. But in the best case, like
yeah,
there
that's
has to be a certain distribution.
I agree to your suggestion. Yeah, I have no problem with that. But because you have shared this, now I will share with all the people in the group so that they can take a look. No problem. Thanks for that. Okay, now come to question number 2. This is fairly numerical question, simple question on deep nets. So you please take a look, and what I would like to know from you, at least from first layer to second layer, what is the number of computation, and then you can sort of straight away generalize for other layers. So you let me know what would be the number of these operations from first layer to second layer.
So can you please repeat your question?
Did you understand the problem statement?
Yes, sir.
Yeah, I mean, if you can compute the whole thing, that's good. Otherwise, what I'm suggesting that what would be the number of operations from input layer to the first hidden layer, till first hidden layer. Okay, from input to first hidden layer, and then the same you can apply for the other layers. But just to make things small, so I suggested that. You only need to take the forward pass using a mini batch.
So the size of the hidden layer is not specified.
You build a fully connected neural network with 10 hidden layers with ReLU activation. So you have 10 hidden layer, each layer has 20 neurons. I mentioned that in the problem statement.
Oh, sure. Sorry, I'm seeing the wrong problem.
Mm-hmm. So can you tell me for one neuron how many operations you need? One neuron in the hidden layer, the first hidden layer. You just tell me that, and then I think we can straight away solve this.
So there would be 100 W, so 100 multiplication.
Okay.
And plus 100 addition.
99 addition.
99 addition plus 1 for bias.
Yes,
Okay.
200 in total.
Okay. So 100 multiplication, 100 addition.
Yes, sir.
Okay, and then what else? You have other operations also.
Sir, and one like max operation.
Okay. Okay, all right. So then for the fast layer, fast hidden layer till like from input to output, input to fast hidden layer, how many operations you need total?
201 for 1 neuron.
So it will be multiplied by 20 then.
It will be multiplied by 20.
Right, right. And then basically you can straight away compute for other layers. I hope you won't have any difficulty if you apply the same thing from second layer to third layer and so on and so forth. Okay.
So in this case, the input layer has 100 neurons, right?
Input layer, you have 100 features here. That's right. You have 100 features, so of course you have 20 neurons in the input layer.
No, sir. I mean, the number of neurons in the input is 100, right?
Yeah, it's 100.
Yeah.
It's the number of neurons and the number of features that you have.
Sir, will it be 201 into 50 into 20? Because
201
into 20 into 50 for first layer. Like
50, why 50 is coming?
because of that mini batch.
Okay, you train the network with minimum size 50. Yeah, so this is for a single.
Is after calculating the forward pass for a single data point, we'd have to multiply with 50.
Right. Yeah, you have 50 minibits. Yeah, so there are 50 points.
Sir, can we say that the number of multiplications will be the number of weight parameters between the neurons?
Sorry, what?
The number of multiplications will be the number of weight parameters. I mean, the weight matrices, number of parameters in those weight matrices. Because uniquely between every two neurons, there will be a weight which will contribute to one multiplication, given that we are taking input layer to be 100. So uniquely, a weight between two neurons will contribute to one multiplication, right?
Say again.
Sir, what I am saying is the number of multiplications will be same as the number of parameters in weight matrices across the neural network.
Number of multiplication would be same as the number of size of the weight matrices in the network.
Yeah, yeah.
That is what you were suggesting.
Yes.
Okay, so from from input layer to the fast hidden layer, you have the matrix size is 100 cross 20, right? The weight matrix size. All right, that's the size of this.
Yes. Yes, sir. Yeah, 100
fast.
cross 20. So there will be 100 cross 20 multiplications in that particular.
Right.
Similarly for the other layer. So it is just the number of weight parameters we have, right?
Okay, I haven't verified that. Maybe yes, you need to check it.
Sir, I think we also need to add bias terms.
No, I'm talking about multiplication.
Multiplication. You are just doing addition operation.
Yes, sir, it would be equal to number of weights.
Yeah, maybe yes. You just check it here. Okay, any other doubt from anybody?
So the max operation is there for evaluating ReLU, right?
Max operation?
Max operation is there for evaluating ReLU, right? ReLU function.
Yeah, ReLU. Yeah, for ReLU you have this max operation. Yeah. Okay. So next, consider question number 3. I believe this is very straightforward. I don't think we need to discuss it. Okay. Okay, all right. I hope this is like it's a very trivial question, so everybody should be able to answer.
Sir, it should be n+1, right?
Yeah, it's n+1. Yeah. Now move on to the fourth question.
So I guess using locally weighted would be better.
Okay, let me hear from others what others say, and then we will try to understand the reason behind it.
I do feel locally weighted would be better.
Okay, all right. Is there anybody who thinks otherwise? Okay, so can you give your reason, please, that why you think?
Sir, it is because normal logistic regression will cover all cases when there is no rain, when there is low wind speed, every case. But what we specifically need is during that particular, let us say it is raining heavily and the wind speed is high and the visibility is also low. During that particular situations, what will be the most sensible way of deciding? Like we need that particular data. Like we will be having more weight on that data, which matches our current scenario, and based on that prediction should be made instead of considering other data points as well.
Okay, what will happen, say in your training set, you do not have that kind of data, like all the data points are very far away from the one that you have near the airport at that time.
Like weather depends locally, right, sir? So like if you were to use other data points, it wouldn't give a proper prediction as to how the weather would be in that area.
Okay, so how do you tackle the situation in locally weighted logistic regression? Is there any trick you can play to address this problem at least? So see, one way that you do not have to always tell that whether you should land or don't land. Okay. At the same time, you can probably also say that you are like not sure, okay, what the prediction would be. So is there any way we can handle this situation for a case when you do not have enough or like no data?
Sir, we could increase the bandwidth of the function that we'll be using for collecting the data.
We can increase what?
We can increase the bandwidth of the interval in which, like basically we'll be using for the locally weighted one, we'll be using a Gaussian expression. So we can play around with the tau in the denominator to expand. If we don't have substantial amount of data for that specific time point, then we could still use logically weighted regression, but like let's say it's 4 p.m. So I could give more weightage to 3 p.m., 5 p.m. data as compared to 12 noon or 7 p.m. data.
Okay, but then what would be the danger of that using that? But this is an aircraft flying thing. Okay, you cannot simply go and predict, and you can allow your system to make mistakes, and then somehow somebody else will handle this. This is not something going to happen here because this aircraft flying. You have to be very careful.
So we need to have a threshold, I guess. Like if there are sufficient number of points within a threshold, then we need to go with it. Otherwise, we should not, I guess.
So how do you judge from your locally weighted model that, okay, you do not have, your model has very low confidence? How do you judge that?
Sir, instead of providing logistic regression, can we provide a linear regression model and kind of show like the risk meter?
Linear regression model you want to apply?
Yeah, sir, like a landing risk meter. If the risk is low, then you can land, and if the risk is high, and
But why cannot you do that using logistic regression? Logistic regression is just another form of linear regression with additional transformation. Right, inside it you have the linear function, isn't it?
So it only says yes or no. It won't say how sure yes or how sure no, right?
Mm-hmm.
So what approach would be better again?
Mm-hmm. Sorry?
So it will only say yes or no, right? Any logistic regression model. There is nothing like partial. So if like
You
there's
can
90% or more
no,
sure, then
that is not entirely correct. You can say yes or no based on threshold, but then you can also say the probability value, right? In addition to saying yes or no. What is the confidence of your yes? What is the confidence of your no also? Because ultimately you are computing the probability values.
sir, indirectly for the probability models, we'll need the linear regression, right?
Yeah, I mean, of course, inside logistic regression you have the linear model.
So is it like we predict both the things? Like if we give the linear regression model and the risk bar, and as well as that, along with that, we give yes or no. Is it like that?
Yes, it is like that. So you basically use this locally weighted function to build your regression model, logistic regression model here. And then in addition to this, your yes no prediction, you also say the probability value that is given by this your network. Okay, because if there is too much of error, then this probability value will automatically highlight that.
So we can take a prior probability distribution as a metric for that.
Prior probability distribution of what?
Of the samples through which we are making the prediction, of the samples that we already have. Like
No,
fraction of sample, let us say we are predicting it that it will be landing. We'll also take the prior probability of what percentage of landings were made. Like that is a metric.
What percentage of landing what?
So I mean, we'll have a window around our feature, right? And we'll have samples based on that. And we'll make a prediction based on that. No, that is the prediction that we made. Apart from that, what we also show is what percentage of landings so far were made. I mean, you're getting it right. Based on that probability, we can kind of give an insight into it. Let us say if landing was never made, I mean, let us say just 2 or 3 times out of 10 times, it means that now when I'm predicting it will be landing, it is less likely that it happens. Like somewhat like naive Bayes.
Okay, but you only have this much of data like rain, wind speed, and visibility, and then based on that, whether somebody landed or didn't land.
We'll just provide that value, so like we can provide the output of that softmax layer.
Yeah, I think best way to tackle the situation is you save your prediction and then as well as the probability value given by your regression model, and then let them judge whether they want to do. Because in a very safety critical system like this, airplane flying or etc., you need to give both these things, and then you let the human decide what they want to do. Okay. Now coming to your question number 5. Okay, what do you do in a situation like this?
Sir,
Yes.
sir. So basically, like, means it would be, I would go with Mahalanobis distance, because in the only difference between Euclidean and Mahalanobis distance is that in Mahalanobis distance we have the multiplication of the inverse of the covariance matrix, and like between the inner product. So if half of the features are correlated, then they will have a lower weightage in the final distance measure. And means basically in Euclidean, if half of the features are already correlated, then moreover we won't be able to differentiate between the distances. Like it depends upon the values of the other features as well.
Okay, it's a very good answer, but I want to know from others if they have a different opinion. I'm happy with the answer. So if anybody has any other opinion.
So could you elaborate a bit on the third type of distance?
Mononomics. Hello.
Yes, sir.
So mononomic distance inherently uses this variance covariance matrix. Okay, that's what the student mentioned. And because the variance covariance matrix will reflect the correlation between different features, so it will handle the situation automatically. Where Manhattan and Eddington distance, they do not have this thing. Okay. All right. And the last question. Yeah, please go through it carefully.
So,
Yeah, please.
so stochastic gradient descent in itself means that the batch size is 1, right?
I mean, we will also call it, this is called vanilla gradient descent, but the minimized gradient descent we also call it stochastic gradient descent.
Okay, sir.
Sir, will it be 3 mini batch size?
Okay, batch size, you are suggesting batch size to be 3.
Yes, sir. And
And
like it should be like every element should be of one class. Like if I choose 3 must be from different class itself.
okay, all right. Any other response from anybody?
Sir, it depends on how many samples are there for each class, right? Based on that, we need to choose a proper cross-validation, I guess.
Sorry. No, I have given the statistics. I mean, you just limit yourself to the statistics given in the problem.
No, sir, but we don't know how many samples are there for each class, right?
Yeah, you do not know that, yes.
Yeah, based on that, like in some cases, we need stratified k-fold if one class is very low compared to the other two. Like we have things like that, so it depends on how.
So even in a non-uniform case, what will happen, right?
Yeah, in that case, like we can uniformly distribute it among batches.
Yeah, uniform case, what the student suggested, what do you think? That this is a good strategy to do that? Okay, so in a uniform case, say equal number of samples you have in a situation like this.
So I think for uniform case, the method which was proposed seems fine.
Sorry.
For the uniform case, the method which was proposed seems fine to me. Like,
Seems fine. Yeah. Yeah, I also think so. This is also fine. So is there any different opinion on this?
So like, but are we allowed to state such a like possibility? Because like generally in real life scenarios, like we don't find out all the labels which are of one class, and then like we generally do a random shuffle and we do mini batch size, right?
Yeah, that is true. I mean, in real life you do not do that, but you know, this kind of scenario, for example, you assume a particular scenario, and then this kind of scenario is very helpful to analyze the behavior of any algorithm that you are proposing. Okay, so when we kind of try to analyze any behavior, because stochastic gradient descent, how it works, is still very unknown for any arbitrary data. Okay, but at least if you know for a particular scenario what the behavior would be, then that give you some handle to analyze your algorithm. And from that perspective, I just give this simple example to work out.
Okay, so got it.
Yeah, because till now, how actually the stochastic gradient descent works, why it works on a very large network, is still unknown. So people do not know that. Okay. So I think that's it from my side. Few questions.
So I have a doubt. So are you suggesting that the answer should be 3?
3 for assuming the uniform case, the good batch size should be 3, and then 1 from each class you use to form the batches.
Yes, sir, but in mini batch, don't we like randomly shuffle and then take the batch?
Randomly shuffle, where you are taking a single epoch, every
Yes,
epoch,
sir.
then you randomly shuffle it for sure data. But the batch formation, I'm talking about the batch formation only.
Yes, sir, but how will we guarantee that we'll have one row from each class?
Oh, okay. So what you do, you randomly shuffle the data from every class. Okay. You just stratify it. You have the class labels and you stratify the data, randomly shuffle this data, and then take one from first class, one from second, one from third, and so on. Okay.
Okay, sir. Yes, sir. Got it.
Yeah. Okay, all right. That is from my side.
So I have another logistic related request. So could you please postpone the deadline for the decision tree assignment, since next week is the test week and the previous assignment is also actually very difficult.
Professor
It's
Oddoy
taking time.
Mitro, Oddoy, I think he posted assignment. Oddoy is, I'm not sure whether Oddoy is there or not. Oddoy, are you there?
Sir, I don't think Professor
So
Mitra
Oddoy is
is
not
joined.
here. So what I will do, I will request you send an email to Oddoy because decision tree covered by Professor Oddoy Mitro. So I request you to send him an email or a message requesting to extend your deadline. Okay.
Okay, thank you, sir.
Okay, all right.
Also, sir, in test, these kind of question will be there. That, like we have to provide our reasoning and like why our
Yeah,
answer is correct.
some questions will be numerical in nature. Okay, that you have to basically give the number. Some questions will be MCQ. Some questions you have to give the explanation and reason. And one thing that I'd like to tell you is that in case that in any question that you have to assume anything beyond what I have said, okay, please you state your assumption and then work it out. Because in case I might have made some mistakes in the problem statement, skipping a particular assumption which were actually required. That might happen on my part. So in order to avoid that, you please, whatever assumption you have to make, you think is reasonable, you do that, make state that assumption, and then you write down your solution. Okay, so that I don't
We
miss
have
out.
to.
Yeah,
So we have to type answer in Moodle.
you have to type the answer.
Okay.
Yeah. There will be a text box, and you can type it there. Okay, all right. So good luck with your examination next week. And you know the time, right? Already on Tuesday from 8 to, I mean, we probably will start at 8:10 or so. And like this is going to be 1.5 hour examination. So. Okay, all right. Shomodipto, maybe you can
Yes, sir.
start your presentation, please.
Yes, sir. Sir, am I audible?
Yeah, yes, you are audible. Yeah.
Okay. So I'll just open my share tray. Okay, so is my screen visible to everyone?
Yes.
Okay, so before going into the actual codings, the actual notebooks, so I'll just touch upon some of the basic theories of the Adaboost and the adaptive boosting and the extreme gradient boosting. So I believe Professor Mitra had covered some of the theories, the theoretical aspects of these two boosting techniques in the lectures.
Yes.
Okay. So anyway, I just skim over some of the ideas. So yeah, as you have already learned, the Adaboost works with basically decision trees of depth 1, or basically decision stumps as they are called, and it assigns different weightages or different importances to each stump. So when we are forming the ensemble, we are actually assigning, so basically each stump has a different weightage when they're when they're producing the final prediction or the final classification. And the way you form these stumps, these learners, these stumps or weak learners, whatever you may call, when you are doing this, is you are basically propagating the weakness of one stump and then creating the subsequent stump. So the weakness means actually the data points or the samples which were misclassified by one stump. So the importance of those samples are actually raised, and so as to propagate those errors to the next to the formation of the next stump. And yeah, that is how you do it until and unless you have a good enough ensemble, and that is how you move into the classification. So this is the basic algorithm. you can go through the actual paper by Freund and Shapiro from 1995, and I'll just go over the steps, the basic steps which result from this algorithm. So this is a data set, and here it is actually as you have probably already learned in class. This is basically the binary classification Adaboost. And yeah, so we have a data set which has basically a yes no type of categorization. So the default borrower is basically the class which we are trying to predict. We have a homeowner, marital status, sex, and income attributes, and it starts by assigning an equal weightage to each of the samples, and then it forms it forms the decision tree, and it basically picks up it basically uh, constructs the decision trees and picks the tree with the minimum error rate. So the error rate is basically you add up the weightage of those samples which were incorrectly classified, and the tree with the minimum error rate is picked, and then you calculate how much weightage you're going to assign to that particular tree that you have selected. So that is basically what alpha t is going to give you. And this half log 1 by 1 minus epsilon t by epsilon t, this is actually an expression which comes out from the mathematics. So I'll go into briefly the mathematics for this, just to give you an idea. And after you compute the importance of this tree, so you have alpha t from the error rates, and then what you do is you update the weights. So you update the weights of the samples so that you can do that propagation of the weakness of this tree to the next tree when you're constructing the next tree. So you update it using this particular formula. So what you do is you see you have this expression here in the exponential. So you see you have the yi, and there's the alpha t for the importance, and the ht, which is basically the output of the tree. So suppose you have for a binary classification case, suppose you have something like -1 and 1 as the output. So one of two possibilities. So say, for instance, a sample is correctly classified. So what would happen is this would either, these two signs would be the same. So for instance, say like this could be in the case that both of them are 1, both of them are +1, yi and ht are +1. So we basically have an e to the power minus alpha t. So what it does is essentially it sort of brings down the weightage of the correctly classified samples, and for the incorrectly classified samples you have a mismatch of these outputs, right? So the yi may be something -1 or ht will be +1. In a scenario like that, what would happen is you would have a positive exponent. So it will bring up the weightages of the incorrectly classified samples. And obviously, since we are talking about weightage, so obviously you would have the summation of those weightages to be equal to 1. So you have to renormalize the weightages accordingly. And before you go on into making the new stump, you can do one of two things. So you could basically do a weighted Gini indexing for each of the attributes, or you could do something like this. You could generate a random number. So this is basically a probabilistic approach where you do something like this. You generate a random number between 0 to 1, and if a number is between, say, so you have the updated weights here, right? So you have the updated weights here, and if the number lies between 0 to say 0.083, you choose this sample, and if it lies from 0.084 to 0.166, you choose this sample, and so on and so forth. And by doing this thing, what you get is you get another data set from the original data set where the chances of the incorrectly classified samples appearing is much more. So you will see that there will be duplicates in the newly formed data set wherein the duplicates are basically the incorrectly classified samples. So in a sense, you are putting more emphasis on the incorrectly classified examples, so that the tree which you are going to form in subsequently, that tree can actually learn those examples correctly, because you know, you will have these weights. Uh, the weights will be calculated accordingly. So that is another way to do it. So one way is the weighted gene indexing, because you already have the revised weights, the updated weights, and another way is to do it like a probabilistic sort of manner. And yeah, that is how you make the trees until you have a sufficient or the required number of trees, and then you can basically move into the classification, where you can just see that like what is the class with the maximum number of maximum amount of weight. So basically that will give you the output class. And I can share the presentation here with you. You can go through this mathematics. So basically we are working with an exponential loss function. So an exponential loss function is being used to calculate like how good the classifier is working, the Adaboost classifier. And by this is where you get the expression for the alpha. So by minimizing the error, you basically get the expression for the alpha. So that's how you get the half log 1 minus epsilon t by epsilon t. And you could also go through this paper, which talks about the mathematics a little bit more. And it's just basic calculus. I mean, it's nothing really big. These are just expressions. So you have the c m minus 1 is, this is just the summation of those basically these weights, the importances of the outputs of each of the trees, and the output itself. So it's just a summation which gives you the output. So yeah, so that's how you get the expressions which you're working with when you're computing the importances and the outputs of the trees. And another thing which we will see in the example when we are running the code is that the Adaboost classifier, the method, the object actually takes in another parameter called the learning rate, which is a hyperparameter which you can set on your own. So this what it does is, it is like another separate shrinking parameter by which you can actually tune the contribution of each of the trees. So what you do is, you already have the alpha, right, which you saw, the alpha t, which determines how much importance you are associating with each of the trees in the ensemble. So by multiplying that with the learning rate parameter, the hyperparameter, you're basically again sort of controlling how much importance you're going to achieve. So this is going to be equal for all the trees, right? You're setting this manually, whereas this is being computed on the fly as the classifier, as the method sort of iterates through each and every model in the ensemble. So this is another thing which can help you sort of to generalize better. It's just like the learning rate which you have seen in the other fields of machine learning, in deep learning and so on. And yeah, so it depends highly upon the number of estimators. So estimators as in the number of trees you are making in the ensemble, in the Adaboost ensemble. And generally their technique is, when the number of trees are high, the learning rate would be correspondingly be a lower value. So that's what is said in this last point. We use a smaller value of the learning rate for large number of parameters, large number of trees, stumps. So yeah, that's just the basic. I'm pretty sure you have gone through this theory. And to go into our example here, so basically we are again using the flower dataset, the iris dataset, which I am sure Deepan had covered in the previous tutorial. So the same dataset, and you can bring in the dataset into your project. And here basically from sklearn.ensemble you are importing the Adaboost classifier. the predefined library, and you're creating an object here called CLF. And here we are basically doing something called k-fold cross validation. So basically you are splitting up your data, the iris data set. So here you have the x and y, the data, and then the target classes. So basically splitting up the data into 10 splits, and you're doing this 3 times. And the random state here basically just sort of specifies like it deals with the randomization of the splits, so where the splits will happen. So it's like it serves as a seed to create that randomization. So you do a tenfold cross validation, and you can run this. It takes a little bit of time depending on the data set. Yeah, so the accuracy is around 94.7% with a standard deviation of 0.056, because the standard deviation is coming because for each of the trials, right? And here you can actually after you do this is pretty much all you require to do the k-fold cross validation, and looking at the accuracy the classifier is giving. But if you want to say you want to predict for a single unseen data point, you can also fit it using the dot fit function. You have seen this probably in the previous tutorial. It's the same for decision trees as well. So you can fit it, and here by default the number of estimators is 50. The number of trees, the estimators is basically the trees. So you can actually access the individual trees, the individual stumps which we saw. The individual stumps can be accessed by this estimators list object, which is inside the CLF object. And if you want, you can also so from a visual point of view, you can also print out the individual trees. It gives a little error because there are more than 20 figures in this list. So yeah, you can print each and every one of these trees, and you will see that these are all the stumps, trees of depth 1 with 2 leaves, basically what we saw in the slides. And yeah, so like Adaboost classifier, which we did here, we did Adaboost classifier here. We can also do an Adaboost regressing, which is basically just fitting and predicting an unknown value, unknown sample, sorry. So here you can feed in any row, any random data points. So 4 features, and the corresponding class will be determined. So you have 3 possible classes here, 0, 1, and 2. It just gives a prediction of 1. And so you can play around with a few. So here in the subsequent sections, we can actually play around with a few of the parameters, of the Adaboost classifier object. So you have things like you can play around with the depth. Okay, so right, like we saw here in the slides, that you have depths of 1. You can also increase the depth of the individual estimators. Okay, so that can also be done. I mean, it's nothing different. I mean, you just saying that after this depth, you just end the process of creating the tree. So yeah, you can do that. So here, as you can see, I've created a dictionary type of data set, and the individual models, okay, so the individual models here, I am actually creating 10 different models. So by models, I'm talking about the ensembles themselves. So 10 different ensembles. So in each ensemble, the maximum depth of each of the trees in the ensemble will be determined by this I. So basically, I running from 10 to 110, like 10 to 100 at steps of 10. And yeah, so then after creating the models, I have a separate method for the validation. It's basically the same thing which we saw above. So just the stratified k-fold cross validation, and you can run this. Yeah, so it gives you these values for each of the 10 depths, and you can plot them, I mean, as per your requirements. If you're working on, like, if you're wanting to see the difference, the variations with the depth or the variation with the number of estimators. So yeah, you can also do that. You can also do so here in this uncommented code, yeah, you can also vary the number of estimators. So if I say I'm taking the same range. So again, starting with say 10 up to 100 at steps of 10. So number of estimators is being varied now. And yeah, so you can again generate the accuracies for each of the different types of estimators. So each model, so in the first model you have 10 trees and 20 in the next, 30 in the following one, and so on up to 100. And you can see that the accuracy it varies. It stays more or less the same, 94 point something. And yeah, you can vary it as much as you wish according to your requirements. And also the learning rate is also a parameter which you can play with. So it's pretty much similar. I'm leaving that to you. You can also play with that. And yeah, that is pretty much what I have to show for the Adaboost classifier part. And you can see there are pretty much a lot of similarities with the decision tree classifier things, because it actually references the decision tree classifier. I mean the decision tree methods, the modules like the fit and the predict and all things like that. You can also print the individual trees. And okay, so that covers the Adaboost part of the presentation. And before going into gradient boost, before going into the extreme gradient boost or the XG boost, I'll just like to talk about the gradient boost. So I'm pretty sure Professor Mitro has also you have learned about this. This was discussed at length. And yeah, so the idea is here also it is very similar to the Adaboost. Okay, so here also we have an ensemble of trees. We have an importance attached to each tree, but here the importances are all equal. So the learning rate which we saw here in the Adaboost thing, although this does not figure very explicitly in the actual Adaboost algorithm. Okay, so okay, before we talk about the gradient boost, I'll just talk about one thing here, just a small mention of the actual algorithm that's being used over here for the Adaboost tutorial that we saw over here. The algorithm which you saw was a multi-class variation of the actual binary classification Adaboost. So this is basically what is known as, I'll just open this paper for you just to see that this is the SAMME, or the stage-wise additive modeling using a multi-class exponential loss function. So this was from a paper from 2006, which actually extended the two-class Adaboost algorithm. And this is the actual algorithm. I can share the paper with you. You can have a look as to how they have actually adapted the original algorithm to multi-class. And the difference, actually the major difference comes here in the calculation of the alpha. So here you can see the same expression with the log 1 minus error by error. So the epsilon, they have named it as the error anyway. But the difference is this additional term of the log k minus 1, where k is actually the number of classes, capital K. And this comes, if you look into the actual mathematics, so this comes from the multi-class loss function, multi-class exponential loss function, which they have mentioned. It's also there in the name. So this is the ordinary loss function which they have used, which Freund and Shapiro used in the binary two-class classification Adaboost from 95. And here this is actually the loss function which they use in this paper, the SAMME algorithm, stage-wise additive modeling. So this, if you do the math, if you do the same differentiation of the error based on this loss function, and then you reduce, minimize that, and then you actually get that expression of the alpha which you saw. So exponential of 1 minus 1 by k y times f. So f is basically the output of the model. So that is what gives you the additional log k minus 1 from the mathematics, and it is more or less the same thing. It is just otherwise it is more or less the same thing. If you understand the basic 2-class Adaboost, this is just a mere extension. And so yeah, so that is what is being used in the Python, the sklearn libraries when you are creating an Adaboost classifier object. Yeah, so that was just one point which I wanted to cover. And okay, now we move into the gradient boost, which I was talking about. They just started. So yeah, so here basically you are also assigning importances to each of the trees, except that the importances are all equal. So that is what is basically known as the learning rate. Okay, so you're multiplying each of the output of the classes with the learning rate. And here you are not explicitly like you're like Adaboost, it is mostly generally work with decision stumps, sorry. So you basically work with, here in gradient boost you can actually extend the depth of the tree as per your requirements. So what we are trying to do here is we are trying to actually minimize the residuals. Okay, so the residual is basically the difference between the prediction and the actual output, and the residual is given by this different derivative of the loss function with respect to the prediction actually. So yeah, this is just a statement of the gradient boost algorithm. And if you actually break that down, if you actually do the math and break down the procedure, so this is what happens actually. I've just made this small diagram. So what happens is basically you start with a data set. You have some output values here. So let's say they are like let's say this is going beyond the binary classification thing. Okay, you have say multiple values. You want to predict some value, say height or income or something like that, and you can construct. So you start with an average of these outputs. Okay, so average of y, and then you construct a tree here where you actually you basically what you do is you so you compute the residuals with respect to the average of the y's. So you basically find the residuals here, and then you use the residuals to actually calculate the tree, the first tree in the ensemble. So it's just the same thing. You're just replacing the output here in the dataset with the residuals and using the same decision tree construction algorithms to construct the decision tree. And you will see that for instance, here you can in this node, this leaf node, you have these two residuals. I mean, this node results in these two leaves with the R1 and R5. These two residuals at this leaf and R2 in this leaf, and so similarly for this leaf, this node as well. And you can average out these values of the residuals to give the actual output of this leaf. So if a data like propagates along this direction, basically you will give the output of the tree as the average of these two residuals. And so basically how you compute the similarity, so how you compute the so how you do this, how do you do this split is actually you compute the similarity score of the basically the similarity score of the node. So you start with a node which has all the residuals here, and then you compute the similarity score, and then you actually take different types of splits, and then you compute the similarity score of those individual nodes which result from those splits. So here you see you compare the similarity scores of the various splits, and then you compute the gain in the gain of that split, and you choose the split with the max gain. So that is how you construct the tree, and then correspondingly you have the residuals in the respective leaves. And in computing the similarity score, you have another parameter here, which is the regularization parameter lambda. So lambda actually, as you have probably learned about, the lambda parameter actually prevents overfitting. Okay, so that's another difference with respect to with respect to say Adaboost or the usual gradient boosting approaches. So there is a lambda parameter here, and so you repeat that with repeat it for the child nodes, and you get a tree first, and then you actually, what you do is you again recompute the residual. So what you do, you actually uh, have the average value, then you add it with eta times the output of this tree, and you get the revised residuals. And based on that, again, based on those residuals, again you repeat the process until and unless you reach a condition where the residuals are below a certain threshold. Like you say that, okay, the residuals are negligible enough for me to end this process, or you have a sufficient number of trees, so a predetermined number of trees. And yeah, so the loss function here is this function, which basically has a lambda here. Actually, it's not shown here. So it's basically a sum of the loss function and plus the lambda times the output. So you have the regularization parameter in the loss function, and these are just some a few points regarding the XGBoost. You can also prune the trees based on a separate parameter gamma. So you can prune. So you can have a random number gamma, and you can compute the difference between the split gain of the split gain of the lowest node in the tree. And if the difference is negative, you prune it, or you retain it if it is positive. So again, you go to the node above it, and you again compute that difference with respect to the gamma parameter. And again you prune or retain it depending on whether the node below is pruned or not. So you can actually do that to actually like reduce your tree and have a more compact structure. So that is a parameter which you can set manually, and it basically ranges from 0 to infinity. So you can have that. And so here, when you're computing the output, so it's basically that you also have the regularization parameter here as well. So that is how it. So if lambda is some non-zero value greater than 0, so you can see that the denominator increases, and you can actually have the outputs sort of being brought down or being shrunk, so as to prevent overfitting. Yeah, so these are just basics of the XGBoost approach. And here also you can do this in code, and you need to bring in the XGB classifier and so basically the packages from XGBoost. You need to install this prior to running any code. So you can bring in the XG classifier and the XGB regressor, similar to the Adaboost classifier and Adaboost regressor. And you bring in some of the additional libraries from sklearn if you want to train, test, split, like splitting the data set or calculating the accuracies. Again, it's the same data set from the iris data set from before. And again, here you can see you have basically a regressor type of thing. There's a small warning here. Yeah, so you can fit the regressor, and similar to the Adaboost classifier, you can also predict. So .predict is also a viable option of predicting the output of any unseen data. And similar to that, similar to the previous validation approaches, the evaluation approaches, you can also do a 10-fold, k-fold cross validation. And It takes a little bit of time, as we saw before, and it's the accuracy is around 94.7% with a standard deviation of 0.053. And you can also plot the individual trees here. So here the plotting is a bit different. You would need to have another library installed, which is the Graphviz library. So I'll just show you this briefly. So you can go here. You need to sort of download the packages here. You can, these are basically executables. You can run this and it will actually give you the option of putting the necessary libraries on your system environment path. So you need the Graphviz function if you're willing to see some of the trees, the actual plot of the XGBoost trees. So you can index the trees here, and yeah, so you can index the trees as num trees, this num trees value here. So I've given 5. So you can view the trees, each and every one. I'm not printing all of the trees here because it's just too much of space. So this is one of the trees, and if you sort of zoom into this, so you will see that the names are not shown here. The F1, F2, F3, these are basically the features. They have just indexed the features as Fi something. So you can actually pass the features. I've not shown it here, but you can actually create a feature map or an F map as a text file. You could try it out as an example, as an exercise. You can actually pass that feature map, and you can actually see, like, you can actually replace the names with the actual feature names. So that's just from a visual point of view. So yeah, so that's one thing. And similar to the Adaboost classifiers which we saw, we can actually play around with the learning rate, which we saw in the slides, the lambda parameter, and also the gamma parameter. And so for here you can see I'm basically varying the number of estimators or the number of trees which I want to have in my ensemble. So I run these two classes, and it's just doing the same thing. It's just varying the number of trees in the ensemble. So for 10 trees, I have an accuracy of 96% and 20, 95.1, and so on and so forth. So yeah, so you can play around. You can I have commented these variables here. You can put them in this code, and you can tweak this as you like, and you can see the variations, and you can also plot it using the matplot libraries as per your requirements. So yes, so that is pretty much what I had to show you for this tutorial. I hope this will be a sort of introductory lesson in order to help you when you're writing code using these boosting techniques. So yeah, that's yeah. So if you have any questions, you can ask. So are there any questions? Hello? Hello, am I audible?
Yes, sir.
Yes. So, are there any questions regarding this tutorial?
No, sir.
Okay. So, okay. Are you sure? So, no questions regarding this tutorial. Okay, so in that case, I'll just conclude this session, and I'll upload the files that you've seen here, the presentation, and also the paper which I briefly mentioned. You can go through the mathematics if you wish, and you can go through the code. You can modify it and work with it. And yeah, so okay, so that is all for today. Okay.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.